Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for the introduction. This is joint work with Vladimir Kolesnikov, who's here. So I'll be talking about improved OT extension for transferring short secrets. So I guess we all know about secure computation by now. There's Alice with our input X, and there's Bob with input Y. This is two-party secure computation. They want to engage in a protocol such that they only learn respect to outputs, but they don't learn anything else other than nothing else is leaked. Right? So this is the most general problem in cryptography, and it's an area which is moving fast from theory to practice. And as we will see in many talks in this workshop, so this is the major research effort, which not only improves asymptotic but also focuses on concrete efficiency. And even in the first talk, we saw there's work which addresses implementation as well as systems issues in this area. Let's take a quick look at the state of the art. So on the theory side, we have really amazing results. So you can do MPC, two-party secure computation, let's say, with constant overhead. So this is independent of your security parameter, independent of, I don't know, pretty much everything. So it's constant overhead over the size of the circuit that you're evaluating. So that's it. So this has been done for GMW via ICOS 08, and also Yao, there's a very recent paper. You can also get optimal communication as well as round complexity. So here optimal means it's just length of your input, does not depend upon the circuit size. And this you can do using like tools like fully homomorphic encryption, indistinguishable deobfuscation. So there are several new results coming there, just 2 rounds for any number of parties. And we also have ORAM-based secure function evaluation, where you don't have to go through the circuit-based paradigm, so you can get your function evaluated in its actual running time. On the practical side, we've had a lot of really cool optimizations about like Yao garbled circuits, let's say free XOR technique, garbled row reduction, point and permute, and flexible XOR later in the day. And there have also been like very, very good implementations, a lot of tricks there. And so now you can garble an AES circuit in 637 microseconds. It's amazing. There are also a lot of optimizations for GMW. This was kind of the GMW comeback that was referred to in Yehuda's talk. So GMW, as we saw, it's one paradigm which easily adapts to the multi-party setting. And my talk can also be viewed as a GMW comeback kind of thing. There are also other hybrids, such as you can get some techniques from Yao and GMW, put them together, and get some more optimization. So that's also there. So anyway, the main point of the slide is that although we have had a lot of really cool results, theoretical results in the last 5 years, let's say last 2 years, our implementations still rely on Yao and GMW from 1980s, right? So one reason is that, well, these are all theoretical results. The constants are very high, but there is also some kind of hierarchy of efficiency here, which we need to take into account. So let me just say FHE is greater than PKE, which stands for public key encryption, and symmetric key encryption, and then the one-time pad, where greater than means that the cost of LHS is and will probably always be by orders of magnitude bigger than the cost of RHS. So this is just something that you see when you implement things in practice. And the topic of this talk, OT extension, is motivated by this major gap in efficiency between public key primitives and symmetric key primitives. So I'll detail on that more as we go. So we'll motivate the problem of introduce and motivate the problem of OT extension. And so in this talk, I'll briefly explain Ishii et al.'s OT extension solution, and how we provide a new framework for it, and then improve both in asymptotic as well as concrete terms. Right. So this is a slide about the big gap between public key encryption and symmetric key encryption. So public key primitives, when I say public key primitives, I mean like primitives like key agreement, oblivious transfer, secure function evaluation. The parties do not have any shared secret in advance, let's say. And symmetric key primitives are like pseudo-random generators, hash functions, etc. So public key primitives are harder to implement heuristically. We have very few candidates. They're all algebraic in nature. We have like, I don't know, DDH, RSA for a long time, and then we had LWE. They're usually more expensive to implement simply because there are better algebraic attacks known against these candidate schemes. So your parameters have to be much bigger if you want to defeat state-of-the-art attacks. Whereas for symmetric key primitives, it's very easy to implement heuristically. You can have like competitions, I don't know, every year, and you can get great hash functions which are just impossible to break. So they're much cheaper in practice to get. So this kind of phenomenon also has some backing from theory, which says, I mean, there is this great result by Impagliazzo and Rudich, which says, loosely speaking, public keying primitives cannot be black box reduced to secret key primitives. In a very practical, the meaning behind this is that there's like a big factor of like 3 to 4 orders of magnitude difference between public key primitives and symmetric key primitives. And this is only made, I don't know, bigger because nowadays Intel provides AES, a new instruction set inside the chip, so AES becomes even more faster. Right? So from this slide, you see that the state of the FR is pretty bad. You know, the public key primitives and secret key primitives, there is like an inherent gap, right? So what is the next best thing that we can do? So we know that you cannot get public key primitives from symmetric key primitives, but maybe we put some public key primitives on the other side, and maybe this is possible, right? So this is known as extending primitives. So I think Yehuda mentioned in his talk, extending public key encryption is very easy. Right? So you just encrypt the payload with the symmetric key. So you use one public key operation, and then the rest is all symmetric key encryption. So you encrypt the payload with the symmetric key is all symmetric key operations. Then you encrypt symmetric key with the public key that's like one public key encryption. And this has had like a huge practical impact on everyday use of encryption. And a natural question is, okay, can we also do this for other primitives? Let's say oblivious transfer. So let me explain the problem of oblivious transfer. So you have a sender with 2 inputs x0, x1, and there is a receiver with the selection bit r. At the end of the protocol, Alice does not know anything about what Bob's selection bit was, and Bob receives exactly x sub r. He does not know x sub 1 minus r. So OT is like is one of the simplest non-trivial primitives. It's very powerful. So in Yao you have this like direct interpretation where you just select one out of 2 things. So you select 1 out of 2 garbled keys, and this allows for secure function evaluation. In GMW, the interpretation is slightly different. So here you look at oblivious transfer as a mini protocol which allows you to evaluate AND gates. So in GMW, you evaluate each AND gate in the circuit using an OT protocol. So let's look at the cost of oblivious transfer. So we saw there's no black box reduction from OT to one-way functions, but like the public key encryption extension, right? So here, if you have OTs on short strings, then you can get OTs on long strings. This is essentially the same as the public key encryption extension. Right? So here you want to do OTs on x0 and x1, which are very long strings. So you just do OT on the short string, which is a seed to a pseudo-random generator, and you just send the masked pads in the clear, and then you just allow it to retrieve one of the 2 seeds. So that is OT length extension. The more non-trivial problem is OT instance extension. So where you start with a few number of seed OTs, and then you want to get like many OTs. So the surprising result here is that OT instance extension is actually possible, and you only need an additional n symmetric key operations, and this kind of result has had a huge impact on SFE. So let me do a quick literature survey on OT extensions. So as Yehuda said, the first OT extension was done by Beaver in a very, very simple and elegant construction. But it was a non-black box use of a pseudo-random generator. So it was kind of inefficient in practice. This was later improved by Ishai, Kilian, Nissim, and Petrank, which I'll call the IKNP construction. So, so they made black box use of a hash function. So it's like you can either look at the work as being in the random oracle model or a special type of hash function known as correlation robust hash function. And it is, till date, it's the most practical OTA extension. I mean, there are, of course, other schemes which build on top of it. But, there have also been other results which improve the efficiency of OTA extension for the in the malicious setting. And there are also other results which help us improve our understanding about feasibility results for OT extension, like how many seed OTs do you need, whether you can do adaptive security, and stuff like that. So in this work, we will focus on improving Semihonest IKNP. So in the next part of the talk, I'll be giving a brief overview of Ishai et al.'s OT extension construction. And I'll actually use slides from Yuval Ishai's talk at Crypto to 10 years ago or something like that. So the IKNP strategy is okay. So I need to perform n number of OTs over, let's say, strings of some length. Right? Then the first and the main step of the reduction is to look at, is to perform k instances of OTs now. So here you wanted to do n instances of OTs selections, but now you do only k instances of OTs, but the string length is very large. Right? And then you can, in your second step is the length extension step, which we saw earlier. So, so now you can make all these long strings into short strings. That is easy. So let me describe the first step, the main reduction. So, so here the receiver picks a random n by k matrix, which is called, let me call it as T. And then the sender picks a random k-bit selection vector, which is called S. Right? So the receiver is now going to start preparing the inputs for the OTs. So the first input of every pair, so it has k pairs of strings are of length n. Right? The first input in every pair is going to be the corresponding column of T. So T1 there is the first column of T. The second string in every pair is going to be the first string masked with the receiver selection bit I. Okay, so maybe this will become clearer soon. So that's it. So the first column is always the receiver's random matrix column, and the second column is that column masked with the receiver selection bit. So anyway, so the OT is carried out. So the sender chooses one out of these two columns. It's going to obtain this matrix, which we'll call it as Q. So it will obtain one column from each of these two columns. Right? So let's first ask, what is this matrix Q? How does it look like? Right, so we'll look at the ith column of the matrix Q, and then so I'm going to argue that the ith column, the ith row Qi is the value is going to depend upon the receiver's selection bit Ri for that thing. So if Ri equals 0, then the two bits in each pair are going to be identical, because R is just 0, Ri is 0, so you XOR with Ri, so you still get the same bit. So in this case, the ith row is just going to be, it doesn't matter which one you select, it's going to be the same, it's going to be Ti, where Ti is the ith row of T. And when Ri equals 1, you can see that it flips depending upon the value of S, whether S is 0 or S is 1. So it becomes Ti XOR S. And the observation here is that the receiver knows Ti, but it does not know anything about the sender's input S. So in the first case, it will know Qi, but it will not know Qi XOR S. And in the second case, it will know Qi XOR S, which is Ti, but it will not know anything about Qi. So you essentially set up your correlations in the right way. So now all you have to do is just you have to make sure to destroy the correlations across different rows. So use the random oracle or some suitable hash function h, and so you're going to generate your masks as h of qi or h of qi XOR s. So these are going to be your two masks, and then the receiver side unmasking is straightforward, is in the normal way. So let's look at the IKNP cost. So the main reduction which I saw earlier, so here you just see that it's just sending xi0 masked with h of qi. So it's the length of xi0, which is L, let's say. So this is OT NL is n instance of OT on strings of length L. So the main reduction which I just described is going to cost just 2 NL bits. It's just masking the inputs and then sending them. And whereas the length extension, which was there in the original strategy slide, that costs 2 NK bits. So this is again a standard reduction. So if you look at the communication cost of the resulting SFE when you try to plug in IKNP construction, you see that okay, if you want to use in YAO, then the strings that you want to transfer are actually keys. So in this case, your L equals K. And when L equals K, you can see that the main reduction and the length extension have the same cost. It's both 2 and K. So it seems kind of nice. Whereas when you want to use it in GMW, here L equals 1, so it's just 1 bit. And you see that the cost is, for the main reduction is 2n, whereas for the length extension is 2nk. It's like, something is wrong, right? So the main reduction was the non-trivial part, but then it costs really low, whereas the cost of the OT extension is dominated by the length extension, which is 2nk. So this maybe gives us some hope, like maybe there's something we can improve here, at least for the case when L equals 1. So in the next part of the talk, we'll talk about my work, which is providing a new framework for IKNP. So we start by taking a closer look at the IKNP construction. So we saw that the receiver is going to choose this matrix T, and then it's going to prepare the inputs for the OT by using one input as the column from T and the other input as the column in T XORed with R. So let's separate these two matrices. Let's call it this matrix is T, this matrix is U, right? So in effect, you can see that the matrix U is just T XOR a matrix R, which is just the selection vectors column wise. Right? So this is actually T and U are secret shares of this matrix R. Now, if you look at it row wise, you see here. If you look at the matrix R row wise, we see that when Ri equals 0, all the rows have the same bits, right? And when R equals 1, it's just all of them are 1s. So you see that there is like this row wise encoding which is going on, right? So 0 is going to 0 to the k, 1 is going to 1 to the k. So at some basic level, IKNP is using repetition encoding. Right? So this raises the question: okay, can we use other more efficient encodings? Because repetition encoding is a very low rate encoding. Right? So the first modification that we have to make is that okay, now we want to use better codes. So we want we no longer can use Ri being either 0 or 1. So we want Ri to come from a bigger domain. So let's say it comes from the domain 1 through m, and then we are going to use some code C. So let's not fix it right now. So this code C is so earlier it was 0 to 0 to the k. So now we want Ri to go to C of Ri, and this will be in 0 1 to the k. And so this is what so the receiver gets R1 through Rn. These are all m-bit strings. I mean they come from the domain 1 through m. So it first creates this matrix C of R in this way. Then we just follow in the footsteps of IKNP. So we ask the receiver to secret share the C of R into T XOR U. And again, the sender is going to pick one out of the two columns. It's either a T column or a U column. And once again, we look at row-wise. We look at how the matrix that the sender receives looks like. And we see that in this case, with the slightly more sophisticated thing, we see that Qi will be Ti XOR C of Ri bitwise ANDed with S. So just as a sanity check, let's see what happens when C of R is like the repetition code. So when C of R was the repetition code, if Ri equals 0, then C of Ri equals 0. 0, 0 to the k, and 0 to the k bitwise ANDed with S is just 0, so it's just Ti. So it's the same as before, Qi equals Ti. And when C of Ri is, when Ri equals 1, then C of Ri is 1 to the k, and bitwise ANDed with S is just S, so it's Ti XOR S. So it's the same as before, it's just, you just added an extra layer of encoding here. And the sender sends like all the different, all possible masks, but now there are a total of m inputs, and he uses the m mask to mask all of them. And then the receiver once again unmasks using Ti. It only has Ti, it does not have anything else.
Now when you say the sender sends and the receiver outputs, are you doing like a 1 out of MOT?
Yeah, I'm doing a 1 out of MOT. Yep. So just a very short security analysis. So at least in the main reduction, you have perfect security against a malicious sender, in the sense that the sender does not receive anything. It's just sending stuff. I mean, it does receive something from the OT, but those are all random independent shares. And you get statistical security against the Semihonest receiver. And this is because there's no loss in security unless the random oracle is queried on exactly one of those points. It's the same analysis as IKNP. And the loss in security comes, I mean, it's m times 2 to the negative d, where m is the number of number of masks that you had, number of 1 out of m selections, right? And d is the minimum distance of C. So what we saw is that we have now got 1 out of MOT, and the cost of 1 out of MOT is 2nk plus mnl. So previously IKNP's cost was 2nk plus 2ml, so now we made it mnl. And then we have the standard reduction where if you want OT n instance of OT on L-bit strings, then you can use, this is standard 1 out of 2 OT. You can get it from 1 out of MOT. Now you have lesser number of instances, but the strings become slightly longer. And then you have this equation for the communication thing. So now what we have effectively done is that we have introduced another variable m, and now we can optimize like using the best value for m. And so this will be the final cost for 1 out of 2 OT. So this is how you, even though the construction is for 1 out of MOT, you can transform it into 1 out of 2 OT using standard techniques. So in terms of concrete efficiency, we use the Hadamard codes for the encoding, and this will give you a factor 2 improvement directly for 1 out of 2 OT, and also for GMW. And there are also some additional optimizations which you can do in the length extension side to give you a factor 3.5. So here I haven't said, so you also get an improvement for 1 out of MOT directly. If you use our construction, that will be like factor 5 improvement or something. The asymptotic communication cost is also, you can get a log k improvement, but this is improvement only over IKNP. There are other, I mean, when you're talking about asymptotic costs, there are much better constructions, but those are purely asymptotic, not necessarily concrete. So in conclusion, so we started by saying the problem of OT extension is motivated by this huge gap in efficiency between public key primitives and symmetric key primitives. And OT extension attempts to bridge this gap, and this has had a huge impact on the practicality of SFE, especially when you're doing secure computation over billion input size, like when the size of the inputs is like a billion bits or more. And in this talk, we proposed the coding theoretic framework for IKNP, and so this can be instantiated either with random oracle or some new type of hash functions, which we call as code correlation robust hash functions. So using the appropriate code, you can get improvements for GMW for 1 out of 2 OT, for 1 out of MOT. And this also brings back the issue of the GMW comeback, because there have been some recent results which have showed that GMW, I mean, although it has been thought that Yao outperforms GMW very easily because of latency issues and stuff, but some experimental results and some more additional optimizations have shown that GMW can be competitive or maybe even outperform Yao. Thank you.
We have time for questions. So actually, I'm not sure if you said it, but what is the right value of n?
It's so if you put m equals k, you will get somewhat close, but it will not be exact. So k or log k or something like that. But when you're doing concrete values, you just have to choose the value of m. So it does not necessarily. You just have to enumerate over the right value of m for this value of n and k. So something like that. So here, like for k equals 128, we think we use some values of n equals 9. Or for k equals 128, we had to use n equals 9 or some m equals 9 or something like that. There's no direct correspondence, but for the asymptotic improvement, like m equals k or something should give you. So you put m equals k, you get n over log k directly. But there is also this other, the log k shows up there, and there's a log k there. So it's not very clean.
But here you're not counting the cost of the c dot is, right? So because if
No,
you increase m, then the c dot is will be more expensive, no?
If you increase m,
Yeah.
this counts the c dot is, right? So that the 2 and k is the c dot is.
Oh, okay.
The m and l is the main reduction. 2 and k is the same as IKNP, is still 2 and k. So there's still the 2k. But n now reduces. You just have to do lesser number of OT instances on slightly longer strings.
I think the last point you raised about Yao versus GMW, in what way can we potentially hope for GMW to be better than Yao? Are we talking about concrete efficiency, computational, or communication complexity?
I think both. I mean, for example, this work you show that if you only need to do OTs on like 1-bit OTs, then you don't necessarily have. So in Yao, for example, when the circuit is small and wide, and you have a lot of inputs, you have to do a lot of OTs, and these OTs are on like 128-bit strings. So these are keys, right? Whereas in GMW, if you want to do the same thing, you just have to do OTs on 1-bit strings. And for example, that is where you can apply our results, and then you can get like factor 2, factor 4 efficiency improvement directly.
The sender's input to your OT are much shorter than Yao. Yao no matter what security parameter,
Yeah.
So in Yao you have to in Yao you have encryptions. You have 4 ciphertexts for every gate. They're big, relatively. So even if it's not necessarily on the input side, also on the sides of the circuit. Of course, if it's a deep circuit, you have lots of ping pong and you're far away, then it won't be good.
There is also the issue of online, offline phase, right? With GMW, you can pre-process all the OTs before the inputs are known, and then the online phase is very.
I think it depends on the
Yao.
circuit. I mean, if it's too deep,
Yao also you
I
can
mean, the ramp
process the
of
garbage.
expression-
it depends.
The circuit,
It can
right?
depend.
Yeah.
With GMW, you can have information theoretic.
Yes.
GMW can do information theoretic for every gate, you mean?
Yeah, once you pre-process the OTs, OT correction is just information theory.
So, can you combine your technique with the optimizations that Yehuda was talking about? Have you checked that, or this new encoding does it mess things up?
With
That's an interesting question.
what? With the transpose, matrix transpose?
Yeah, there was a couple of things. There was some, I guess, system. We had the
I haven't thought
transpose.
about it.
One, or the fact that you were using random, so you don't either.
So the random thing is also one of the additional optimizations which I just did not elaborate upon, but that you can do. That is just inside the OT extension itself. But the transpose. No.
Also, about the GMW versus Yao, our paper with Ranjit, he mentioned, but he didn't emphasize. So roughly our estimates were about 3 times smaller computation for Semihonest model for this hybrid. where you use multiple rounds, compared to the best Yao.
And the savings again comes from the fact that gates you don't have to do.
Well, yeah, right. So the cost of Yao is that you have to encrypt the garbled table.
Yeah.
GMW or with the hybrid that we were using, there's no garbled table.
Yeah, this is a different work, right? So where you do information theoretic YAO. So this is like short depth circuits. You can just do it information theoretically. You don't need encryptions of encryptions. And so for every 3 levels, you just need to do 1 OT. So one level of OTs. So there you get like factor 3 improvement, for example, directly.
Are there concrete functions that we're thinking about when we're comparing GMW and YAO?
Right?
Are there concrete functions? When you have all this data, what functions are you computing?
That would be for any function.
Sorry?
For any circuit.
I think that's going to be a very long. I mean, that's a very big program. So let's thank Ranjit again. And, so our last speaker for this session is Frederiksen from Aarhus University, and he's going to talk about MiniLEGO, efficient secure two-party computation from general assumptions. I heard it's a good paper.
All right, thank you for the introduction. So I'm Thor Frederiksen. This is a joint work with Thomas Pelle Jacobsen, Jesper Buus Nielsen, Peter Sebastian Nordholt, and Claudio Orlandi. So what I will be talking about today is the MiniLEGO, or efficient secure two-party computation from general assumptions. So what I will go through today is a little bit of an introduction, which will be quite short, since most of the stuff I will introduce we have already heard at least once today, this morning. Then I will go through a few tools we need, and then I will give an overview of the Lego construction, and then give a bit of details. And I will end up with some conclusion about practical efficiency and future work. So first of all, as we all know, secure computation can be based on many different things, such as secret sharing, homomorphic, both semi and fully homomorphic, garbled circuits, and so on. Some of these approaches are secure in the passive setting, some are secure in the active setting, and some can be made secure in the active setting. And I apologize for all the papers I have forgot to put up on here. So anyway, the setting of what I will be talking about today is based on Yao's garbled circuit and the cut and choose paradigm Professor Lindell talked about earlier today. This will be used in combination with XOR homomorphic commitments to yield a UC secure OT hybrid protocol for secure two-party computation. So first of all, a little outline. We already talked about garbled circuits, so I will quickly remind you what it is again. We have two-party functionality, where each party has some inputs which are bit, and one party or both parties wish to learn the output. For simplicity, we can assume that just one party learns the output, since we have several results generalizing this to the case where the other party should learn the output. So the function we'll be looking at will be working on bits, and thus we can express it as a Boolean circuit, which is a bunch of wires and a bunch of gates. The circuit can then be garbled by having one party. In this case, we can assume it's Alice. Select random keys for each of the wires, where a key represents either 0 or 1. And then she can garble each of the gates using these keys. This will, in the end, yield a complete garbled circuit. And it's possible, in the end, to associate something we call the output decryption table for the output wires, such that the person evaluating this garbled circuit can translate the keys he learned from the evaluation to some actual bits. So with this in mind, the passively secure protocol is quite simple. We have one party, in this case Alice, garble a circuit. She sends this garbled circuit to Bob, along with the keys corresponding to her binary input for this circuit. Alice and Bob can then execute an oblivious transfer, where Bob inputs the bits for each of the wires for the circuit, and Alice inputs the keys in such a manner that Bob will, in the end, learn the keys in correspondence with his binary input. Thus, he will have a key on each of the input wires for the garbled circuit, and he can evaluate it all the way down and use the output decryption table to learn the actual output. So this is only secure in the passive case. One very straightforward attack is the fact that nothing makes sure that Alice actually garbles a circuit computing the functionality the parties have agreed on. She So you could, for example, garble a circuit where if Bob first bit is 0, it outputs garbage, or if his first bit is 1, then it actually computes the function. So one way of making this scheme secure is by using the cut and choose paradigm, which basically means we do the passive, well, in very broad terms, means that we do the passive protocol several times. So in this case, we have a corrupted Alice construct many garbled circuits. Some of them might be constructed correctly, and some of them might be constructed wrongly. Wrongly meaning that they compute a different function, or they are not possible to evaluate at all. Alice then commits to all of these garbled circuits towards Bob. Bob selects a random challenge of selecting, for example, half of these garbled circuits to be verified. With this challenge, Alice opens these garbled circuits, and Bob can then check that the garbled circuits are in fact correctly constructed. If that is the case, then he believes Alice is a nice person and continues with the protocol in which Alice can send the keys in correspondence with her binary input to the remaining garbled circuits. And again, they can do Oblivious Transfer in order for Bob to learn the keys in correspondence with his input. In the end, he can evaluate the remaining circuits, and he takes the majority of the output to be the actual outcome of the computation. So this is the overall idea of achieving active security of Yau's garbled circuits using the cut and choose paradigm. I'm abstracting away a bunch of different issues here because, as Professor Lindell mentioned earlier, once we introduce cut and choose, we also introduce a bunch of new issues, but such as this selective bit attack, consistency of input, and so on. But this is just, so I will not talk about that. This is just to give an overall idea of the cut and choose paradigm of garbled circuits. So what can we say about this? Well, it's relatively simple. We don't really introduce any significant new cryptographic primitives or anything like that. We use basically statistics to make sure that what happens is correct, at least on top of the security of the passive protocol. And it's also quite fast, also in particular, since we don't introduce a lot of new fancy stuff. Unfortunately, it's the speed, both in practice and in asymptotics, is quite bad. We get an increasing complexity of O of S, where S is a statistical security parameter. So we need to garble many circuits in order to actually make sure that this approach is secure. Now, the idea of LEGO takes departure in trying to optimize this, which means that we will reduce the overhead from O of S to O of S log the circuit size. So this basically means the larger the function we wish to compute, the less amount of garbled gates do we actually need to make. All right, so that was a little bit overview. Two things we're going to need before we actually show how to show the actual LEGO approach is the idea of the free XOR, which was also covered earlier today. So instead of having random keys on each wire in the circuit, the keys are constrained. The 0 keys will be random, and the 1 keys will be defined to be the 0 key XOR the global difference, which we call delta here. This global difference will be the same for each garbled circuit. From this, it means that if we encounter in an XOR gate in the circuit, the output of that XOR gate is then defined to be the XOR of the 2 0 keys entering the gate. So we will need some kind of circular security here. In the same manner, the 1 key of the output of an XOR gate is defined to be the 0 key XOR delta. So this basically means once Bob evaluates the garbled circuit, if he encounters an XOR gate, he simply takes the XOR of the 2 keys he has, and that ends up actually being the correct output in correspondence with the XOR function, which can be checked by just writing out the truth table in the cases. The other thing we're going to need is XOR homomorphic commitments. So in a general commitment scheme, we have one party, Alice, put a message into a box. The box is then locked with some sort of key. The box is sent to Bob. Then they can do whatever they want to do, and at a later point in time, Alice sends the key to Bob, Bob can open the box and find the first message. So that's general commitments. In the case of XOR homomorphic commitments, we assume we have more than just a single commitment. So Alice might put another message into another box, locks it with another key, sends this other box to Bob. And then at a later point in time, she actually wants to open to the XOR of the two messages, M1 and M2. So she takes both the keys, does an operation on them, sends this to Bob. Bob takes the boxes, does an operation on them, and uses the keys, and what comes out would then be the XOR of the message M1 and M2. So it's basically what the name suggests. It's commitments with a homomorphic property with respect to the XOR operation. All right, so that was a little bit about, yeah?
That's just a functionality requirement, right? Is there, how about the security requirement? Is just the usual ones?
Um,
Require that after you decommit, you only learn the XOR and nothing else?
Yeah.
So you do have addition.
Yeah. So that's just the overall idea. All right. So with these tools in mind, I can introduce the idea of the LEGO approach. So instead of having Alice garble many garble circuits, we have her garble many gates. In particular, it will all be AND gates since we use the free XOR approach. It means that we can also do NOT. An AND and a NOT can give us an AND, which is a universal gate. So this is sufficient. So just assume we only do AND gates so far. So Alice makes many AND gates. These gates will, like in the normal garble circuit, consist of a garble computation table. But it will also consist on XOR homomorphic commitments of the 0 keys of each wires in this gate. So this means that we will have for each gate, we'll have the garble computation table, and we will have an XOR homomorphic commitment to the left 0 key, to the right 0 key, and to the output 0 key. And again, as Alice might be corrupted, some of these gates might be wrong. So they might not compute the AND functionality, or they might not compute at all. What happens is then Alice sends a commitment to all the garbled, sends all the garbled gates, the computation tables, and the commitments to Bob. Bob chooses a challenge. So, for example, he chooses half of these gates to be verified. Alice opens, and Bob checks that they are in fact correctly constructed. If that is the case, then he thinks Alice is a nice person and wants to continue to play with her. He discards the gates he have already opened and thus have a bunch of garbled AND gates remaining along with XOR homomorphic commitments to the 0 keys. Now what then happens is that instead of constructing many garbled circuits, he constructs many fault-tolerant gates. So he selects some of these garbled gates at random and puts together into a bucket, which can be viewed as a fault-tolerant gate. So this is basically, the bucket is more or less a sub-circuit, just computing one gate, where it takes the majority of the outcome of the gates inside. So this basically means assuming only a minority of the gates in the bucket are badly constructed, the bucket will evaluate an AND gate correctly. And since we do many garbled gates and we construct these buckets at random, except with very small probability, in fact negligible probability, we will only have a minority of bad gates in each bucket. So Bob does this for all the garbled gates he have left, and ends up with a whole bunch of these fault-tolerant buckets. He then combines these buckets into a fault-tolerant garble circuit. So he puts these buckets together to form a garble circuit, the garble circuit they wish to compute, and then does some sort of soldering in order to connect the wires of each of these buckets. Finally, he completes another kind of bootstrapping process for the input wires, which we call the input soldering, to make sure that each wire actually has a key from the beginning. Then he has a fault-tolerant circuit consisting of these buckets. It should here be mentioned that XOR gates and NOT gates can be injected into the wires here. So in the end, they can do as in a normal garble circuit, where Alice sends the keys in correspondence with her input, and Bob can learn his keys through an Oblivious Transfer. Thus, at the end, Bob will have the keys for each of the will have one key for each of the input bucket or each of the inputs for this garbled circuit, and he can evaluate it top down and thus learn some output keys, which he will in this case send to Alice. So in this case, unlike the normal case, we assume Alice is the person who actually learns the output of the functionality. All right, that's the overall idea, and that was very abstract. So I just said we do some magic soldering in order to make these buckets and then magically solder those buckets together. So let me go in a little bit of further detail in regards to that. First of all, consider the case where Bob makes a bucket. So he has a couple of garbled gates, and he wants to solder these together into the fault-tolerant bucket. So this means that he won't actually know the keys. He will know the commitments to the 0 keys in each bucket, along with the garbled computation table. What he does is to designate one of these buckets as the head, just assume the first one. And then what happens next is that we will use the XOR homomorphic property of the commitments. So he will ask Alice to open the XOR of the 0 key of the left wire of the head bucket and the 0 key of the left wire of the second and of the third bucket. So this basically means the head will act as sort of a pivot. So what he will learn here, as I said, is the XOR of the left 0 key of the head and XOR with the left 0 key of each of the gates in this bucket. This will also be done for the right keys and for the output keys. All right, let me clean this up a little bit. It's getting a bit messy, so let me show you what Bob knows. This is what he knows. He has the garbled computation table for each of these 3 gates, and for each of the wires of the non-head gates in the bucket, he has associated that wire 0 key XORed with the corresponding wire 0 key of the head of the bucket. This is one of those things. It's not technically that complicated, but it's really hard to just get your head around it. I'm trying to portray it as good as I can, but all right. So I'll just repeat it one more time. Each of the remaining 2 buckets will have the 0 key corresponding with that gate, XORed with the 0 key of the head of that bucket. So this basically means that the keys getting into this bucket and the keys coming out of this bucket will actually be the keys of the head gate in this bucket. So this means that if Bob is evaluating the bucket, what he will get into it is either the left 0 key or the left 1 key, the right 0 key or the right 1 key, depending on which value is actually supposed to get into it. So this means that the head, he can just evaluate directly. He has 1 key on each of the input wires to that head, no problem. Now here comes the fun thing, and this is why we need the free XOR approach. To evaluate the other gates in this bucket, he takes the keys he get into the bucket, which are the keys for the head gate, and XOR it with the openings he knows. So this basically means that the 0 key of each of the wires in the head gate disappears, it XORs out. We will in both cases consider the left wire here, have the left 0 key of the head gate and the left 0 key of the head gate here. Those 2 will disappear, and what will remain will be the left 0 key of this particular gate, either alone or XORed with delta if what gets into the bucket is a 1, is supposed to be a 1 key. So basically, it's just making the 0 keys related to the head disappear, and then what remains will be the same semantic. It will have the same meaning, each key, but it will be based on the 0 key on each of the wire in the remaining gates in the bucket. And this follows directly from the free XOR approach. So this means that in the end here, Bob will have a key for each of the input wires to the remaining gates in the bucket, and he can thus evaluate them. Regarding the output of each of these gates, the same approach follows. We have the 0 key for the head of the bucket and the 0 key for each of these gates opened down here by Alice. Again, he takes the output of this bucket, and the 0 key from the head will get XORed out, and the 0 key from this bucket will then get XORed out. What will remain will be the 0 key of the head, perhaps XORed with 1 if the output of that gate was supposed to be a 1. So it's basically masking with the 0 keys from the head and then making it disappear in the end. So this means if all these gates have been constructed correctly, in the end we will have the same key for each of these gates, and thus we can take the majority to be the actual output of that bucket. All right, so that was constructing a bucket. Now we also need to put the buckets together. The principle is the same. Again, we have the output of the top bucket here to be the 0 key of the head, XORed with 1 if the output was a 1, and just the 0 key if it was supposed to be a 0. Then we have a new bucket, and we wish to solder the output of this top bucket to the left wire of this bucket. In the same manner as before, we ask Alice to open the XOR of the 0 key of the head of the left 0 key of the head of this bucket down here, XORed with the 0 key of the head of the top bucket. The 0 key of the output of the top bucket XORs out. What remains will be the 0 key of the bucket J, and perhaps XORed with delta if it's supposed to be a 1. All right, the final part is the input soldering, and this is again the idea is the same. Each of the inputs to this fault-tolerant circuit will either be given directly by Alice, or it will come as part of some sort of OT. What we'll then do is that we will have the input to this input soldering being the left 0 key of the head here, and then what we do is ask Bob is to have Bob ask Alice to open the left 0 key of the head XOR with the right 0 key. So this basically means now he has 1 key for the left wire. He can take this XOR with this. The left 0 key XORs out, and what will remain will be the right 0 key or the right 1 key, depending on whether or not what he got in was 0 or 1. Now he can evaluate the head directly, and since AND is the identity function, 0 and 0 is 0, 1 and 1 is 1, this will work directly. The rest of the soldering of that bucket is just like before. So that was the overall idea, and how we actually construct the soldering of each of the gates in the bucket. I'll just give a little conclusion. So practical efficiency. Well, we get, compared to the general cut and choose of garbled circuit, we get better asymptotic complexity. We reduce the amount of garbled gates we make with a factor log of the circuit size. However, we need these XOR homomorphic commitments. Many of these for each of the garbled gates. So this means that unless we construct a humongous circuit, it will actually depend directly on the efficiency of how we can do XOR homomorphic commitments. So in the original approach to LEGO, which is by Nielsen Orlandi from 2009, in fact, it wasn't XOR homomorphic commitments that were used. It was Peterson commitments, which is additively homomorphic. So in that paper, public key operations were used. In the one we have here, we actually construct the XOR homomorphic commitments from an error-correcting code and Oblivious Transfer, which makes it possible to base the XOR homomorphic commitments on non-number theoretic computations. Again, generally, Oblivious Transfer is based on public key and exponentiations and so on, but as we have heard a little about this morning, it's possible to construct a bunch of these using what we call using the OT extension, which makes it actually quite nice and quite inexpensive, assuming we need to do a lot of OTs, which is actually what we need in this case. And since we're actually able to do XOR homomorphic commitment and not just additively commitments, it means that this will work with any free XOR garbling scheme. So point and permute can be used as along with gobble row reduction and all those optimizations. Finally, a little bit about future work. It turns out that even though we make these XOR homomorphic commitments based on just oblivious transfer and error correcting, the constants are still quite large. In fact, it turns out to be around a factor 40 in these commitments, which is, of course, not that nice. So future work will include seeing if we can use a better code, if we can do some way of actually making these significantly smaller. Another interesting thing to look at is smaller replication factor in the buckets. So right now we are still we need a majority of the gates to be good, but as recent research have shown, there's ways to do it, at least with the circuits where just one of the gates, or sorry, one of the circuits are correct. So it will also be interesting to see if we can do that there and get some optimization there. So hopefully in the end it will, we can continue working on it, and hopefully in the end it will be competitive with the general approach. So I'll just end up with a small table of different approaches for this. Yeah, and that's it. Thank you.
We have time for a few questions. Yeah.
Yeah.
I follow the correctness of your algorithm, but I cannot find out how your algorithm is secure in privacy. Is it? Can you show a little justification of how the adversary cannot XOR different outputs together and get some information about them? Because you use the same mask or key for every gate. So
you mean the free XOR approach, or
private?
What?
Are private?
So the free XOR approach is from 2008, and there has been some future work looking into the security of it. I cannot remember the authors, but there was a paper showing that it is secure, assuming circular correlation robustness. But I don't have anything to do with that. This is just some previous work that we use in that manner. Yeah.
Maybe just a historical remark. XOR commitments, when they were first proposed, they were implemented with Oblivious Transfer. And
oh, okay.
embedded Rudy, and later on control graph and tap and many other words.
Okay. Thank you. Yes?
So you said you use error correcting codes and the constants were 40. What are these codes?
They are won by Shen and Kramer. At least there is one by Shen and Kramer that gives the demands we need. Unfortunately, we need to have some quite strict demands on that code. We need it needs to allow some leakage of code words without giving away what is actually encoded, amongst other things. And it also needs to have a relatively large randomization. So this is why it ends up actually being quite large constant. But we're currently looking at optimizing it, and it seems that it will be possible to do with just a random encoding, using a random matrix to encode, as we will not directly need to do decoding.
Let's thank Tora again, and then there is lunch, I guess.
Thank you.